Greetings, one and all. Today we're going to talk about specific heats. You have discussed specific heat in every chemistry class, so I'm just going to add a little physics spin to it. Alright, so adding energy to a material causes its temperature to go up. Makes sense. We put energy in something, all the molecules inside start moving really fast, which we find out in our thermal energy podcast. These molecules bump off each other, and the friction that is between these molecules causes heat, which makes the temperature go up. And opposite of that, if we take energy away from a substance, the temperature goes down. So those molecules slow down, they aren't bumping into each other as much, not producing all that heat, so the temperature is going to go down. When we discuss specific heat, we're talking about the amount of thermal energy needed to raise the temperature of 1 kilogram of some substance by 1 degree Celsius. Now, you can also replace this degree Celsius with degrees Kelvin. So, or 1 degree, well, you don't really put degree symbol on the K, or 1K, because they're both related to each other directly. It's measured in joules per kilogram per degree Celsius. So you'll see specific heat of something be joules per kg degree C, or joules per kg per K. Here are some common substances and their specific heats. Water, which is one we're going to use a lot, is 4,184 joules per kilogram per degree Celsius. Ice is 2,000 roughly. Asphalt, like the stuff we drive on, 920. Glass, iron, and so on and so on. So have you ever noticed that on a hot summer day, the pool is cooler than the hot cement? Now, why is that? So if we look back here, we notice that water, 4,184, while asphalt, concrete, 920. So it's like, more than 4 times as much specific heat for water. So you also might have noticed that the ocean is cooler than the hot sand. That damn sand is so freaking hot that it burns and hurts. So why? So the sun has been beating down on both of them for the same amount of time. So the same amount of thermal energy is getting into those guys. So it takes more thermal energy to raise the temperature of the water than it does the cement. This is because of the higher specific heat of water. So it's going to take more thermal energy to make it as hot as the sand. So that's why the water is colder, because the sand and the water are both getting the same thermal energy put into them, but it takes more of that energy to raise the temperature of the water than it does the sand. Hence, hot sand, burn feet, ouch, ouch. Drum roll, forgot that was on there. So water absorbs a lot of heat energy before its temperature changes, while sand needs little heat energy before its temperature increases, which we just said, and that's because of the specific heat. And because of this, different materials heat up at different rates. So gold needs a lot higher temperature than, or a lot more thermal energy than, sorry, I said that wrong. Gold heats up 7 times faster than aluminum. So gold has a lower specific heat than aluminum. You can actually, I do this all the time, I don't recommend it, unless you're crazy. But put a baked potato in an oven, wrap it in aluminum foil, I can just grab that potato right out of the oven when it's done, because that aluminum foil has very high specific heat, so it's not nearly as hot as a potato inside of it. Got to be quick though, because that aluminum also transfers heat very fast. So back to this. So this gold heats up a lot faster, and all the molecules are moving a lot faster than this aluminum because it has a lower specific heat. Requires less thermal energy to heat up. And these different materials also store different amounts of energy. So water takes about 30 times longer than gold to heat it up, meaning it can store that energy 30 times more of that energy, 30 times more calories to be exact. Because calories, whenever you see those on your nutritional labels, that's actually stored energy. And in this case, we're talking about heat. So that means we can store it in here because it loses that energy slower than gold. That's just why we drink water instead of gold, because that's better for you. Plus, molten gold would probably hurt going down. So we already said the specific heat is the amount of energy required to raise the temperature of a material, some kind of substance. And it takes different amounts of energy to make the same temp in different substances. Gold, water, gold, aluminum. And we call that amount specific heat. Just, everything I said, all in a nutshell. So we said we're going to be talking about specific heat of water a lot. So this symbol C little p is the symbol for specific heat. So C sub p is the symbol for specific heat. So CP is high because in water because the molecules form very strong bonds. It's hard to break those bonds. And it takes a lot of energy in order to break those bonds. And once those bonds are broken, they can start moving around, and this is why things are started heating up, because the molecules break down. Well, they don't break down. The bonds break down between the molecules, and they move around faster and faster. So an example, CP of water is 4,184 joules of energy to raise it by 1 kilogram by 1 degree Celsius. I already said CP stands for heat capacity. And now we're going to learn how to calculate the changes in thermal energy. An equation you should know already. Q equals mc delta T. A little out of order. You can rearrange this however you want. Or get rid of those x's. Q equals mc delta T. Q is the change in thermal energy. M is the mass of whatever substance we're talking about. Delta T is the change in temperature. It's the final temperature minus the initial. It's very important that it's always in this order, because Q can turn out to be positive, Q can turn out to be negative, and that totally makes a difference in your answer. It's always final minus initial. Final minus initial, always. And CP is a specific heat. All right, so if I give you a problem that the mass of some substance is 45 kilograms, the amount of energy needed to raise that by a certain temperature is 203,000 joules. And that temperature, it starts at 28, it ends at 40, because remember, it's final minus initial. This is T final, T initial. And that gives us a change of 12 degrees. So what is the CP? So if we take our Q equals mc delta T, solving this for, that should be big T, solving this for CP, we get CP equals Q divided by m delta T, which I have right there. And you just plug in some numbers. So you plug in your numbers, so you get CP equals 203,000 joules over mass, 45 kilograms, and the delta T, which was 12 degrees Celsius. You can see our units are going to be joules per kilogram per degree Celsius. Put all this in your calculator, and you get 376. A lot of times, too, your heat, your Q, will be given in kilojoules, and your CP can also be in terms of kilojoules per kilogram per degree Celsius. All right, our copper ornament has a mass of 69.3 grams and changes from a temperature of 20 to 27.4 degrees Celsius. How much heat energy did it gain? So I will give you charts like this on the test so you can pick off information. So we're looking for the heat, the amount of thermal energy. So Q equals M, and our mass is 69.3 grams. What is wrong with that? We don't like grams. We want kilograms. We've got to divide that by 1,000. So get rid of that. We're going to make it make it into kilograms. Divide by 1,000. 0.0693 kilograms. Times the CP of what material? Copper, 390. That's another thing you might see too. You might see CPs in terms of, I'm running out of room here. You might see CP in terms of joules per gram degree Celsius too. It's not uncommon. So I had 0.0693 kilograms times 390 joules per kg degrees C. And that's a change of temperature of 7.4 degrees. The final minus the initial, 27.4 minus 20, gives me 7.4 degrees C. Plug that in your calculator, and let's see what we get. I forgot to bring up my handy-dandy little computer calculator. Times 390 times 77.4. And that equals about 200. So the answer is A. Sorry if there's a little hiccup here on your video. Apparently 7th graders can't read signs that say go away. So we'll try this again. So my answer was 200 joules. And here's a chart. I guess that's all that was left. Just a chart. Maybe I'll print one of these guys out for everybody. Just some common specific heats in joules per gram per kilogram per degrees Kelvin, which you can replace degrees Celsius with those. No big whoop. Thank you.